Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel and it also helps us reach others in need of assistance with these topics. So in today's video, we're going to be covering problem 1.1 from Hibbeler's Mechanics of Materials. So we are tasked with what it says here. The shaft is supported by a smooth thrust bearing at B and a journal bearing at C. Determine the resultant internal loadings acting on the cross section at E. So few things that we have to note here is that we are in a 2D system. So when we are in a 2D system, a thrust bearing, we can model that as a pin support, and a journal bearing in a 2D system, we can model as a roller support. So what I can do here is, since I have a thrust bearing, which is a pin here at B, I can just model that as a pin. And then C over here, since we have a journal bearing, we can model that as a roller in our 2D system. And then, of course, we have our applied force of 400 pounds here at A, 800 pounds here at D, and we are tasked with finding the internal forces here at E. So anytime you have to find internal resultant loadings or internal forces at a location, you are going to slice through that location. So this dotted line right here will be our slicing through point. Now, when you slice through, you're going to have options to take either the left side of that cut or the right side of that cut. Or if it's a horizontal slice, you'll take the top or bottom. In this case, we have a vertical slice, so we're either going to use the left side or we're going to use the right side. Now, this case doesn't really matter. You can use either one, and this goes with any kind of problem. Typically, what happens though when you cut through these objects, these members, usually one side may be easier than the other to find internal forces. Sometimes it's about the same difficulty. So I always want to take the lesser amount, which usually means the least amount of forces on one side of the cut versus the other. But if you look at our cut here, what we have is that we have a one force of 400, a support on the left side, and a force of 800 and a roller support on the right side. So it doesn't matter which side we take, it's going to be the same level of difficulty either way. So and in saying that, what you can do is you can take the left side, solve for internal forces, and then check your work with solving on the right side. That's a great way to check your work in the end, is just do the other side that you did not do. So for instance, let's take the left side. Let's take the ABE side here. So when we take ABE, that means I need to know the reaction here at B. Anytime you have supports on your side of the cut line that you are working with, you must find those supports before, before you cut through. So we're going to find the reaction, the vertical reaction at B before we cut at E. So what I'm going to do is I'm going to take my moment at C equal to 0, and this will give me my static equilibrium in order to find my reaction here, which I'm just going to call Y for right now. So summing moments about C, taking the entire member here, I would have 400 pounds. It'll be rotating clockwise about point C, or counterclockwise about point C, which I'm taking as positive. So that'd be a positive 400 pounds times 12 feet, which is the total distance from the 400 to C. And then I'm going to subtract off BY multiplied by its perpendicular distance to C, which is 8 feet total. And that is a negative because it will be rotating clockwise about point C here. And then finally the 800, which will be rotating clockwise about point C as well. So that'd be also a negative 800 pounds times its distance to C, its perpendicular distance, which is 4 feet. And that's all I have in force-wise in moments about point C, so equal to 0. B sub y is my only unknown in this equation, so I can easily solve for it, and it pops out to be a positive 200 pounds. And since it's a positive number, I assumed the correct direction of my reaction, which is up. So technically, since it is a pin, there's also a BX reaction possible here for a 2D system. But do you see any horizontal forces being applied? Because if I do the equilibrium equation for summing forces in the x direction, B sub x is the only thing there, so it is equal to 0. Okay, so now I found my reaction, or reactions at point B, my pin. What I can do is I can cut through E, and I'm going to take the left side of my cut, which will be represented by this line here, my free body diagram, which I'm going to draw here. This is point A, this is point B, and here's my cut E, and there's my slicing through cut. So I'm going to apply my 400 pounds here, my reaction of B sub Y, which is 200 pounds in the upward direction. B sub X is 0, so I'm not going to put it on there. And then I have distances here, which are all 4 feet. Makes it nice and easy. Sometimes drawing the free body diagram takes longer than the actual problem. So remember with internal forces, you're going to have 4 possible. You're going to have normal force or axial force, which is labeled as capital N. You're going to have shear, which is V. You're going to have moment, which is M, or you could have torsion, which is T. Now, in this particular problem, we will not have any torsion in this 2D system. Because what that would mean is that we have some kind of force being applied directly through the screen at you off of the center line, which is not happening in this case. In a 2D system like this, you would have to be told about torsion being applied. You would have to have it shown being applied, something like this being applied there. It's not happening here, so we don't have to worry about torsion in this case. We will eventually go over problems that you do have to worry about torsion later on. So what we're going to do is we're just going to apply these 3 internal forces just like reactions, and we're going to solve for them just like we do reactions. So we're just going to apply them in a direction. So I'm going to apply N going this way. I'm going to apply V going this way, which is my shear, and then my moment like this. So why did I draw them in these directions? Well, this notation right here is considered positive directions for these internal forces. So anytime you have a cut line, you have a member on the left side here. So we're taking our left side. In, which is your axial force pulling away from your cut line, that is tension, which is taken as positive. Shear, if you're looking at the left side, the downward direction is considered to be positive. And this makes a lot more sense when you look at shear moment diagrams, which happens later on in mechanics materials. So for right now, just say, yeah, that's what it is. And then moment when it is rotating on top of your member, on top means positive. So what we're doing is we're just writing these out in the positive form. It makes it a little bit easier for our final answer because internal forces are usually given without arrow directions because the arrow directions aren't going to make a lot of sense because what happens is when you take the other side of the cut, the right side, your arrows will be flipped. It will look like a mirror. So arrows usually aren't used. We used positive sign conventions here for internal forces. Okay, so now we have 3 internal forces to solve for. So how do we solve for these? Just like reactions, we're going to use our equilibrium equations as summing forces in the y, summing forces in the x, and then summing moments about a point. All have to be equal to 0, all have to be in equilibrium. So let's go ahead and let's use the easiest one, which is the horizontal forces. If we take to the right as positive, well, what do we have here? Our normal force N is the only horizontal force that we have in the system. So, whoa, look at that. It's got to be equal to 0. Pretty easy, right? There is no axial forces being applied here. All right, so let's move on to summing forces in the vertical direction, which now we actually have forces being applied. So we have 400 pounds downward, so minus 400 pounds plus 200 pounds going upward, and then minus V equal to 0. But wait, I said that this is positive sign convention. So why am I writing it with a negative? Well, I'm assuming all upward forces are positive, and V is going downward, so it will be a negative sign inside of my equilibrium equation. When V comes out with a value, if it is in fact a downward value, that is considered to be positive shear. These sign notations over here, the positive sign notations for internal forces, are not dictated or are not conjunction here with these. These are totally different. These are which you're using positive and negatives inside the summation equation. And this will make a lot more sense once we get through the problem here. I just wanted to point that out as we go along because I've gotten that question before. So V is my only unknown in this equation, so we can rearrange and solve for it. So V actually pops out to be a minus 200 pounds. in the downward direction. So I have a negative sign, which means my arrow is actually in the opposite direction, which means it's 200 pounds in the upward direction. Okay, so let's leave the arrow on for right now. So we know that V is 200 in the upward direction. Alrighty, so now let's move on to our moment equation, which I'm going to scroll down here a little bit. So moving on to our moment equation, I'm going to take counterclockwise as positive, and the best place to sum moments at for your internal forces is at your cut line most of the time. And the reason why is, well, if you sum moments over here at A, you would have to include V, your shear, because it has a perpendicular distance away from A. Well, what if you screwed up your summing of forces in the Y direction? That means V is wrong. That would automatically make your moment wrong. So the best place to do it is at your cut line. That way V and N are not included. And just in case you got those wrong, it won't automatically make your moment determination wrong. So most of the time, it is best to just sum moments at your cut point. So summing moments at E. Well, I will have 400 pounds rotating counterclockwise about E, so that is positive based upon my sign convention that I have for my summation equation, which is 400 times 8 feet. And then 200 pounds, which would be negative because it's rotating clockwise, so negative 200 times 4 feet. And then V and N have no perpendicular distance because they are right through E. M is a moment. It doesn't need a distance, so we're going to include it. And it is rotating counterclockwise, so it's positive there in this equation, equal to 0. So M is my only unknown. And once I solve for it, I get a minus 2,400 pound feet of moment rotating counterclockwise. So what that means is that it's actually 2,400 pounds or 2,400 pound feet of moment rotating in the clockwise direction. All right. So now that I have my values and I know their arrow directions, here comes how you actually dictate or you actually show your final answers for internal forces. And it's going to be using these positive sign conventions here. So I'm going to write out the full form of positive sign conventions here for internal forces, just to give everyone the best chance possible to get this right for your own homework, for your own test, or whatever you are given in your class. All right. So what I've done here is I've taken a beam and I have sliced it through. So here's my slice. We have the left side and the right side. So this will be normal force, shear, and moment. And these will be positive directions for these values. So normal force will be if it is pulling on that cut line, which technically, if you want me to write it, I could write it right there so we can get rid of this so it's a little less confusing. So if it is pulling on your cut, that is positive. That is positive tension. For shear, if it is downward on the right end of the left segment, that's positive. If it's upward on the left end of the right segment, that is positive. And this will make a lot more sense when you're talking about shear moment diagrams. Moment, if it is rotating on top of the beam, so it will be counterclockwise on the left side, clockwise on the right side segment, that is positive. So we are using left side segments, and this is what we have for our given answers, what we just determined. Well, we found normal force is 0. So we could write our normal force is 0. Our shear, we have found our shear to look like this. In blue, it is 200 pounds in the upward direction. Well, red is showing positive sign convention here. So what that means is my shear is going opposite the positive sign convention, so it's actually minus 200 pounds. And then my moment I have found to be 2,400 pound feet, and it is rotating underneath the beam. Anytime you have that rotation underneath the member and the opposite direction of what is positive, this is going to be a minus 2,400 pounds or pound feet, or you could write it as minus 2.4 kip feet because it is in the negative sign convention. So in total, right here are your answers. You have to use the arrow directions that you get from your cut compare them to the positive sign conventions for internal forces, and then you can apply positive and negative signs appropriately. So a lot of times why I said just go ahead and start them out in the positive sign convention, because that first determination will actually tell you if it's negative or positive, because you already started it out in the positive sign convention. Negative 200. Oh, look at that. Negative 200. Minus 2,400 pound feet, minus 2,400 pound feet. But it's really just up to you what you feel most comfortable doing. It's perfectly okay if you just want to go ahead and assume directions at the start. It doesn't matter. Whatever you get as your answers in the end with the arrow directions, you have to compare them with the positive sign conventions to apply the appropriate positive and negative signs to your internal forces. So this is how you would solve this particular problem. And I hope that explanation works out and helps out. So I hope this video was helpful, and if you want to see more problem solve this variety, please check out the other videos on our channel as we're going to start adding more mechanics of materials problems. Also, if you haven't done so already, please like this video, leave a positive comment below, and please subscribe to the channel because all of that does assist us greatly on this end. Thank you for watching, and I hope you have a fantastic day.